Hello. Good evening, Latika madam. I'm Samarjit from Creative Bhubaneswar.
Hello.
Hello, madam. We will start the session in about 7 minutes, so we have still time. So, do you like to check the connection or slide presentation, or is it okay?
Yeah, I like to share my screen, but I don't find how can I.
So, there will be option of present now. I'm just disconnecting.
Hmm, present now? Okay. Window. Right. Can you see my screen now?
Yes,
Yes,
ma'am.
yes, visible.
It's
All right. So I'm gonna let you start first, then I'm gonna share my screen later on.
sure,
Yes,
ma'am.
yes.
Actually, we have 5 minutes left, so we will wait for all the participants to join. We'll start
Right.
with 5 minutes.
Okay, no problem.
Thank you. Hello. Very good afternoon to one and all, and good evening, Professor Latifa Nurami. Despite there is a time difference of around 2.5 hours, so she has come to join this FDB program and share his knowledge. So, Professor Latifa is working as a professor in ITSN Indonesia, Institute Technology Sheffield, November, Indonesia. So she has done her PhD in École Centrale de Nantes in France, as well as his MSc in Design of Systems and Products in the same institute. So she has won various awards and recognition like IFTOMM Young Delegate Program, Best Researcher and Best Presenter in Indonesia Today Science Foundation, Indonesian American Civil Frontiers of Service. So on the research grant sides, so she has been awarded with Scheme A World Class Professor in 2009 Industry Academia Partnership Program for Indonesia, England. She has been a principal investigator for that, and there are many more achievement on the research grants, awards, and other activities. She has been an active member in various review committees like Journal of Mechanism on Robotics, Mechanism and Mechanics Theory Elsevier, Robotica, as well as she has been a member of program committee at IEEE IFTOMM conference in 2021 Toronto, Canada, co-chair of ASME IDETC Mechanisms and Robotics Conference 2020 in Missouri, USA, and and many more. So I'll not take much time because it will take a lot of time if I spell out all the achievements she has done so far. So welcome, ma'am, and I must thank you for gracing your time to all the participants of this program as well as for as a host. We have been feeling privileged to have you, and we will welcome and we will request you to share your screen and share your slides so that our participants can utilize this session. Ma'am, please.
All right. Thank you very much. How can I do this? I think you have to close yours.
Yes, ma'am. I'm just stopping it.
All right. So, good afternoon, everybody. This is now 4:30 p.m. around 4:34 p.m. Indonesian time. And firstly, I would like to thanks the committee, especially to Dr. Pradhan, who invited me to give talk to this afternoon session. And I would like to say welcome to the participants and thank you for joining my talk. All right, so without further ado, um, what I'm going to present today is mostly about my research. So it's like I would be very happy in this occasion so that I can disseminate my research results. The topic I will talk today is about reconfigurable parallel mechanisms for industrial applications. And I am Latifa. Here's my email. If you like to discuss more in more details, then you can contact me either in Gmail or in official mail. So I'm coming from Laboratory of Engineering Systems and Controls, Department of Mechanical Engineering, from Institute Technology 10 November. Just a quick overview about where I'm coming from. So here it is my country, Indonesia. You probably heard about this country. I've been in India. I've been in Delhi, Bangalore. I attended a conference, IFTOM conference. So IFTOM is professional organization like IEEE, but in the field of mechanisms and machines. And my field of interests are more in mechanisms and machine. So I joined more conferences of IFTOM. So I attended Bangalore 2 years back, 2018 in Bangalore. Then I visited New Delhi. So it's about 5 hours, 6 hours flight. And here is my country. It is an archipelago, many islands, small islands, and we have 5 big islands. And I am sitting in this island. This is the most crowded island in the country, Java. Yes, just like a software name, Java. And here is my city, and you can see, I'm gonna change to laser, right? So here is my institute. We have a very big pond and a big hall to be rented and many departments. I will show you after this. Here it is, the map. If we can see it from the top view, here it is our institute, and Department of Mechanical Engineering is here. So all of this is our institute. We have a department over here, and here is the hall that I have shown you before, the hall to be rented for special occasions, public or even for a private. And in the right picture, this is the front gate of the mechanical engineering department. We have an M symbol for mechanical engineering, and here it is. Our campus is very green. We have many big trees. Well, anyway, this is a rainforest tropical country. So we have many big screens, many big trees, so the students may enjoy while studying with their friends. Again, as I told you, I'm from System Engineering and Controls Laboratory. I'm the head of this laboratory. Here, our staffs and students all together, what we are doing in this lab. So we are doing basically many about controls, not specifically about robotics. So robotics is just part of it, what I'm doing. But my colleagues, they are doing also controls for industry, controls for process plant industry, and many applications. My short biography have been read before, but I want to let you know a little bit. I finished my PhD in 2015. I'm an assistant professor like right now. So my interest is about parallel mechanisms, cable-driven parallel robot. I like to do type synthesis. This is more about design. And I'm doing kinematic dynamics analysis. I'm a reviewer, and I'm an active reviewer of ASME Journal of Mechanisms and Robotics. If you are doing research in robotics, then you will know this journal, Mechanisms and Machine Theory in Robotica by Cambridge Press. All right, so before coming into reconfigurability, we might want to know the basic theory for defining the reconfigurability. I believe you all know about this transformation. We are doing research in robotics. I believe you all know about the transformation. This is the main soul of robotics, is about transformations. And the transformation matrix that I used is basically the same like a Cayley. I hope you know that, the Cayley algebra. And I am using a Cayley or quaternion. Yeah, quaternion is more well known. So I'm using a quaternions. Quaternions is basically homogeneous rather than using Euler angles. Euler angles, you have 3 angles, but somehow you will have a singularity, parameter singularity of Euler angle, or we might call it Gimbal lock. So instead of using Euler angles, I'm replacing it by using a quaternions. I'm using 4 parameters, x0, 1, 2, 3. But if you search in many literature, they are using it with different notations, q0, 1, 2, 3. So basically they are the same. So here it is my rotation matrix, and I have a translational vector d, and I believe you all know this. So d is simply a translation displacement vector x, y, z. And my colleagues, I have been working with Austrian robotician. They like transformations in terms of study. Probably you know this. So study, they even expand the translational parts into 4 homogeneous translational parts. For me, myself, I'm not convenient with that convention, so I prefer to use a displacement vector and rotational matrix in terms of quaternions. So that was the basic. I believe you all know about that. Now let's come to the term reconfigurability. So I've taken it from the paper of Setsi and Lagos. The definition of reconfigurability is the ability of a system, any system. In this case, I'm talking about robotics, specifically about parallel mechanisms. So the ability of my robot to repeatedly change and rearrange the components in a cost-effective way. So without disassembly and assembly it back, I can change to different motion type, let's say, to different orientation continuously. So we call it in a cost-effective way. The very old definition, the oldest definitions of reconfigurability is kinematotropic mechanisms, based on the change of kinematic behavior. So that's why they call it as a kinematotropic. So it is a kinematotrophy properties, and it can change mobility regardless its motion type. So we don't care whether it is 1 translation, 2 rotations, or 2 rotations, 2 translations. We don't care about the motion type, but we care only about the change of the number degree of freedom. And it really depends on the variations of configurations. The example is here. This is quite easy. So here is, this is a spherical and spherical. There is no prismatic in the middle. So this is simply SS kinematic chain. Then if you assemble it all together, you have like 5 legs all together. So you can either make it straight like this, then it will have 2 degree of freedom. You will have translation, right? Circular translation. Or if you twist the kinematic legs, then you have only 1 degree of freedom rotational motions. So this is the definition of kinematotropic mechanisms, the very beginning description of reconfigurability. Okay. Right now, let's continue to second definition. So reconfigurability covers many sub-definitions, and the second definition is metamorphic mechanisms. It depends on, it is not, it doesn't depend, but it is based on the characteristic, the animal characteristic of metamorphisms. So the term was adopted from that. So if we take a look in the right picture, this is basically the well-known RPS. But what is unique is here, the R can be rotated. So the axis of revolute joint can be oriented to different directions. So that's why we call it R small and R capital, because the R small is meant to change the direction of the revolute joint. So if we take a look here in more detail, so we have this revolute prismatic along the way. So the directions of U can be rotated like this due to the rotation about N. So we call this metamorphic joint because once it can be revolute when you fix the discrete rotational of N, and once it can be a universal joint, right? So it is a metamorphic joint. So that if you assemble that into mechanisms, we call it metamorphic parallel mechanisms. So what happens if you are using this kind of metamorphic joint? You will have a change of mobility. I will talk in more detail about this. Then we call this joint as a lockable joint, because after you rotate for some degree, then you lock the small r, so you will get RPS, but the motion of this RPS will be totally different from the previous degree of rotation of the R joint. Then you will get a variations of architecture, obviously, because you are changing the direction of you will get different architecture of RPS. So this paper was published by my colleagues, Dongming Gun, and we met in conference. By the way, conference is a very good event for us to meet with other researchers to collaborate. So I met him in a conference in Hong Kong. Then we have something in common. He has a problem, then I have the tool to solve it. Then finally, I can use my tool to solve his problem. So he has that robot back in his office, but then he wants to know how's the workspace, how the mechanism behaves with the change of lockable joint, with the change of the metamorphic joint. So we are using the powerful tool based on the quaternions. So basically, we divide the architecture into three categories. The first category is, we call it cubical configurations, because theta, if you imagine theta is 0, so all the revolute axes will be intersecting at one point. And at some angle, these dashed lines can be orthogonal to each other. So that's why we call it cubical configurations. And the second configuration is hyperboloid, where theta is within 0 degree and 90 degree. So you can imagine that all revolute joints are skew and they are becoming hyperboloid. Hyperboloid is when you have a thick vertical altogether and you twist it, then you have this hyperboloid configurations. Then the third category, we call it planar configuration. Imagine if you have theta is equal to 90 degrees. So my revolute joint, all my revolute joint will be horizontal. So all my revolute joint will be horizontal. Then the well-known RPS, the traditional RPS, belongs to this category. Right, so after defining one by one all the configurations, now we will focus on the first configurations, cubical configurations. What is unique about this mechanism is, back then when I did my PhD, I was doing a research. I was analyzing the mechanisms of RPS, where all three revolute joints are intersecting in one point, and they are all perpendicular to each other. So we still call it RPS, but we have additional term, RPS cube parallel mechanisms. So this was done during my thesis. And it was done by using an algebraic geometry. This is very powerful tool, algebraic geometry. And everything was done in implicit equations. So basically this point B, the spherical point, the spherical joint at point BI is moving on the plane yellow perpendicular to the axis SI. So I can formulate it in terms of geometry and algebraically, so I get the constraints equations. And then from the set of my constraint equations, I can do everything. I can even do dynamics analysis because those are the basic. Here, my focus was to find the workspace. This was a collaboration with the Innsbruck University, professor from Austria, Innsbruck University. So my workspace, the workspace covered by this RPS cube is a Steiner surface. If you look more into detail about surfaces in mathematics, there are a lot of surfaces, very unique. And one surface here is covered as a workspace of my mechanisms. And you can see in the left animation, this is how my mechanism moves inside the workspace. Yep, this is actually the Steiner surface. I'm going to tell you a bit detail about what it is. So this surface has self-intersecting and symmetrical surfaces. So all the surfaces are symmetrical, and it has lines that intersect all together at one point here. Then 3 points moving on orthogonal planes, and this this concept was actually already discussed by Bottema and Roth. This is very famous book, 1990, Theoretical Kinematics. So if we want to focus more on kinematics, I will suggest you to read about this book, Theoretical Kinematics. So this book was very old, but this book also discussed about 3 points moving on 3 orthogonal planes. And then imagine after some years later, I can cover that those theories are actually existing these days, which is here is my robot. So my robot, the 3 points of my platform are moving on 3 orthogonal planes. And this work has been published in Journal of Mechanisms and Robotics in 2015. And then let's go back to 3 RRPS, the metamorphic parallel mechanisms. Okay, before what I just presented to you was 3 RPS done during my thesis work. And then when I met my partner here, we discussed about his mechanisms, his problems. Then finally, the topic that I covered was a subset of his the first configuration is cubical configuration when theta is equal to 0 and p is equal to some degree, 0 up to 90 degrees. Now we want to see how the platform behaves. Behaves mean what is the shape of the workspace, or whether the degree of freedom, the motion type change with the change of this degree. This is very important. If you want to design something, you want to know whether your platform really target your applications, either for surgical applications or for industry. So this is what we were doing. So here with the change of P, so P is varying from 50 degrees, 45, 54.7 and 60 degrees. How the workspace looks like. It looks like exactly just what I have covered 5 years ago. So my workspace, the Steiner workspace is this one. When P is equal to 54.7, imagine P is equal 54.7, all this dashed line become perpendicular to each other, become orthogonal to each other. So when I change P into 60 degrees, the workspace is still Steiner surface, but it'll be a bit elongated. Or when I change P equal to 30 degrees, then my workspace is becoming flatter and flatter. And this workspace, this work has been published this year with my partner Dongming here. You can check it in ASME Journal of Mechanisms and Robotics. Now, the third configurations, I will jump into the third configurations when theta equal to 90 degrees. This is a well-known RPS. So all this dashed line with an arrow here, they are becoming planar. They are lying on the horizontal plane. And then we want to know how this robot moves with respect to each other. So this robot actually has, we have a new terminology, we call it operation mode. So operation mode is defined by the number of degree of freedom and the motion type. So this mechanism here, it has two types of modes, operation modes. But people didn't know how to distinguish these two operation modes. It has been an issue for this decade, for the last decade. So what we are trying is to reveal how can we distinguish between operation mode 1 and 2. What we have done is by deriving the velocity matrix. I believe you know about this. So A is my transformation matrix. We derive it with respect to time, and we multiply it with the inverse of my transformation matrix. So I will get a velocity matrix. The rotational part is a skew, where you can take the angular velocity directly, and the translational part is the linear velocity of my platform. So now the difference between at the bottom and at the top, these two figures, we can differentiate it by defining the axodes. Um, I hope you already know the axode. So this is just like centrode, the instantaneous center of rotations in the case of centrode, but axodes is instantaneous axis of rotations. So which means imagine if my platform green here is moving with some degrees of rotations and also translate at the same time. So the collection of the axis is becoming like this, the blue surface. We call it rule surface because this surface is generated by lines. Imagine you have straight lines all together, then it makes a surface. And the same here for second operation mode. We define it by using a velocity matrix. We took the components of the velocity matrix, then we can define the axode, how the axis of rotation of this platform. All right, now let's continue with reconfigurable parallel mechanisms. Here is parallel mechanisms. We call it demo robot. It was proposed by Zlatanov, Bonev, and Goslang in 2002 in a conference. So this mechanism, if you take a look closer, each kinematic chain is composed of 5 joints. All is revolute joint, revolute, and all 5 joints are revolute. And then you assemble it all together like this with these configurations. And yeah, here the platform now is in planar motion. Then when you change the configuration of the leg, now you change into 3-degree freedom translation. And then now you change again into a spherical mode about the center point. Okay, so that is actually the concept of reconfigurability. We change the motion type, we change the number of degree of freedom that is possible without disassemble the mechanisms. That is the concept of reconfigurable parallel mechanisms. So we call it operation mode. As I told you before, operation mode is defined by the number of degree of freedom, the motion type, and also the normal factor of this platform. And we don't need a lockable joint. So it is quite different with the term of metamorphic mechanisms. So if we take a look here, there is no lockable joint. There is no metamorphic joints. All joints are moving, and also with the motion of all joints, the platform can change the operation mode. So this robot, it's named Demo Robot Double Y Multi-Operational. It has 3 degree of freedom motions, but it can change to different motion type. And also, to change into different motion type, it has to cross, they call it C space singularity. C stands for configurations, but I call it, with my group, we call it as a constraint singularity, because the robot loses some constraints, so that the robot is in constraint singularities. And the way they discussed and reviewed this mechanism was based on the screw theory, the well-known screw theory. That was for demo. Now, if I have another mechanisms here for degree of freedom mechanisms, for degree of freedom mechanism is quite useful for many industrial application, for pick and place application. They are using 4 degree of freedom because they need to rotate, they need to orient the platform to pick the candy, for example. Then it has to be oriented in some way so that it can be it can be put in a box with the same orientation. So here now I have a 4 degree of freedom parallel mechanisms. It has 4 kinematic chain. We call it kinematic chain, or you can call it lag. There are many terms for that. And here is my kinematic chain. I have a revolute here, then I have U-join. 2 U-join, U-join at the bottom and 2 U-join in the platform, attached to the platform. Okay, and then this mechanism has 4 degree of freedom, and at each the first join at each kinematic chain is actuated with some here's the change of my actuated joint, theta 1 1, theta 1 2, 3 and 4. Now, what is the problem with this mechanisms? We wanted to know how many operation mode. We know that this is very common sense, that the number of degree of freedom of the mechanisms, if it is a fully parallel mechanisms, usually equal to the number of the legs, the number of the kinematic chain. So now we want to know whether this mechanism has another degree of freedom or has another motion type. It is possible. Okay, what is the problem? The problem is these mechanisms, the equations are higher degree polynomial. So if it is higher degree polynomial, then if I want to decompose it by using primary decomposition, it will be computationally expensive, right? And then what we have done, then we decompose the platform into 2 like this. So the mechanism, the platform is decomposable. Now I have 2 types of mechanisms with the same base, but they have a different platform. Now I have RUU, 2 mechanisms with the same degree of freedom. All right, so after decomposing it into 2 different mechanisms with the same base, now I can formulate the constraint equations. We can see here that we have a U joint here and U joint at point C at B and C. And at point B, I have a vertical axis VI, and at point C, I have a vertical axis also NI, but with respect to the moving coordinate. So in some way, NI is not always vertical, but VI will be always vertical. So I can formulate an algebraic geometry formulation that vector VI, NI, and BC, they are always lying on the same plane. So the formulation I used here is actually the parallel piped equations, or they call it triple product. And finally, after formulating my constraint equations, I can do the primary decomposition. And actually, our initial hypothesis was right, that this mechanism can perform another degree of freedom. So the first operation mode is Sonflies. Sonflies was a geometrician, mathematician who invented 4-degree of freedom. So that's why up to now the 4-degree of freedom motion is named after him. We call it Sonflies mode or Sonflies motion. And then the second operation mode is upside down. Well, this is quite imaginary, but in theory, this is possible. In reality, this is probably not a possible one. So you flip the platform upside down, then you can still move it in a 4-degree of freedom motion. And then the third operation mode is when the platform is tilted, like this picture. So this platform is no longer parallel to the base, and this platform is tilted for some degrees. This is probably 20 degrees. So if you have a platform like this in 4-degree freedom motion, and then the platform is no longer 0-degree, but tilted some way, then you have to be worried that it means your mechanism is no longer 4-degree freedom motion, but it has, or it exhibits another motion type. And now, will it be possible for my mechanisms to switch from Sonflies mode to upside down Sonflies mode to additional mode where my platform is tilted? Yes, it is possible. So we can see here. So this is my Sonflies mode where my platform is flat, parallel to the base. Then I have to bring all the legs first to the transition mode. So I have to bring it in this configurations. This is my transition mode. And then finally, when I am in the transition mode, I can tilt my platform like this. So now, like this, in this configuration, my platform is no longer performing 4-degree freedom motions. So when you are using this kind of mechanism for pick and place operation, and finally you are in the transition mode somehow, then you have to be worried that your platform will behave and change to another motion. And then, yep, now my platform even tilt even more. Then finally, my platform is upside down. Again, this is in theory possible. In theory, it is possible, but in application, this is not possible. But anyway, we can see that this mechanism has several operation mode. These 3 cases are possible. Okay, in some way, if you don't know your mechanisms quite well, your robots can behave differently. And this work has been published in 2016 in Mechanisms in Machine Theory. If you want to know in more details, you can check the paper. Right, now let's continue to another mechanisms. That was the mechanisms that I analyzed. Now, in a project that I'm having with my partner in United Kingdom from Salford University, we have a project to build a mechanism for 3D printer of house, 3D printer building. And then we listed the requirements. What are the requirements to be a printer for a building? And now, of course, we will have three translations, but if we are going to use a non-symmetrical shape of nozzle, so imagine if you have a rectangle nozzle, not a square or not a circle area of a nozzle, then it means if I printed, let's say 1 meter, and I have to print another wall, I have to maintain the same thickness of my walls. So I have to somehow add in the corner, I have to change the orientation of my nozzle, right? So it means I need a orientational function of my platform about a vertical axis. That's why we come up with the 4-degree of freedom motion of mechanisms, so that the nozzle can be oriented. And this is a very important requirement that all my motors should be fixed on the base. I don't want my mechanisms to be too heavy, because carrying the nozzle, the mixer, and the dough are quite heavy, and I don't want my mechanisms even more heavy by carrying the motors. So the most important requirements is my motors should be fixed on the base. It is actually the concept of my mechanism. My motors, well, this is not a real concept yet, because we are not going to use this kind of actuators. We are going to replace it with a hydraulic. But anyway, this is the conceptual design of our 3D printer building. And you can see in the right animations, this is how it looks. This is what we printed actually. So the way we designed something is we came up with CAD software, first CAD design, then we printed, and we see whether it works perfectly, whether it follows or it obeys the laws of kinematics and dynamics. Then finally, we build the second prototype. We have several prototypes. The first prototype is by 3D printer. We printed our printer. So now we have a second prototype. It is by using a real motors, but a mini scale. This is the mini scale of my prototype. So I'm not going to show the video yet because it is still not done yet, and this is quite confidential for the project. But I can show the picture here. And here is our motor, 4 motors, and here is the platform. We have a U-joint attached to the platform and attached to the motors. And then we want to know what is the workspace and where is the transition of the transition region, so that the platform will change into another motion. We want to anticipate that. So we formulate the same equations by using the algebraic geometry approach. Basically, these 3 vectors are lying on the same plane, so that we can formulate equations, constraint equations. And based on these constraint equations, we come up with very interesting results. Of course, this mechanism has sunless mode, upside down sunless mode, just like before. And number 3, it has additional mode. And this additional mode is 3 degree of freedom. So actually the degree of freedom degenerates from 4 into 3. And we're going to look what is this 3 degree of freedom motion. So the first operation mode is sunless mode, as we all know before, that this platform here will have 3 translation. We can see it in the transformation matrix. And by the way, how can you define the mobility? instead of using Grubler-Kutzbach criterion, you can also analyze the transformation matrix. Here it is, the way I computed my mobility. The mobility of my mechanism is by seeing the transformation matrix. Here it has 3xyz, which means this mechanism has 3 translations, and the remaining rotational components are only x0 and x3, and here it is 1. So we can see that it has 1 rotational about vertical axis. And the way I define this transformation matrix is quite different. This is a European style, specifically Austrian style, where the homogeneous scale is at the top. Well, you can change it if you are more comfortable. If you want to put this scale 1 to be at the bottom, there will be no different at all. So we call this mode as a sunless mode. And then what else? It has upside down sunless mode. I have shown you before that the platform can be tilted, can be flipped 180 degrees. And we can see from the transformation matrix, the difference is here. You see the remaining here, it becomes -1. Before it's only +1, now it becomes -1, which indicates that the platform is flipped upside down. Parameter. So basically design parameter is here, A, B, C, D. Parameters that defines the length of my platform, the base, the length of my base, the length of my platform. Those are design parameters. So what do these equations tell me? So basically, if I change my geometry, the geometry of my robots, my additional mode will behave differently. Okay. So let's take a look. I have a video here. So now I can make a conclusion in a table that I can switch from sunless mode into additional mode if I give, let's say, when the base is equal to the platform, or when the base is smaller than the platform, then our additional mode will be different completely. So I'm going to show you the video here. So here is the A, B, C, D, the design parameters, and we have 4 types of geometry. You see that the base, we can make it smaller, we can make it longer, bigger, we can change the design parameters. Now, sorry. So first here we simulated in the CAD software how this mechanism moves. Translation. Of course, it has vertical translations. Then it has a rotational motion. And here it is. The platform is in a transition configuration. What happened? Then it switches into different operation mode, which is additional mode. Then we built the prototype, the first prototype that I told you. We built it, we printed and we assembled it with different materials. And yeah, now the platform is changing its behavior from the sunplace mode. Now it is tilting to different operation mode. And well, due to the leg interference, leg collisions, the possible at all. And here we have another theory. This belongs to singularity, but it is actually quite different. So now imagine if you have a mechanism, and then you actuate, or all the actuators, 4 actuators here for the red color. So when you are actuating it, it means that the platform should not be moving. But in self-motion is the platform can have a full motion. So it's different with singularity. In singularity, you have a shaky motion, but in self-motion, your platform will have a full cycle. Full cycle means it has completely new degree of freedom. And in our prototype, we can also show the self motion.
Indonesia's one professor about intense.
Right. Now I will continue with the dynamics. We have shown that this mechanism has several operation modes, and to change from one mode to another, it has to cross constraint singularity. And now we are going to deal with that, but in dynamics level. And we are still working on it, so we don't show the results in this presentation, but I will show the results that we have just presented last month, crossing actuation singularity in dynamics level, and this is possible. So here is the red curve is a singularity loci. Every time my platform touch this loci, this curve, then my robot will be in singularity. The platform will be very shaky, and this is very bad, especially for machining, right? Because in machining you need a very rigid mechanical system. And then we test a trajectory, a simple straight line trajectory from the bottom to the top. From this bottom to the top, this is the blue line, is the trajectory that should be followed by the platform. Now we test 4 types of trajectories. We know the shape of the trajectory is a straight line, but we want to know the change of the velocity and accelerations. So we have tested 4 types of trajectory from degree 1. So we are using polynomial trajectory, and there are many trajectories available in the literature. What we have chosen is a polynomial trajectory, degree 1, degree 3, 5, and 8. So if we see for all 3 trajectories, degree 1, 3, and 5, we need to know the boundary condition, the beginning of the motion and the final motion. What is the velocity, the position, and accelerations. But what is different with degree 8, we need to know what is the velocity and acceleration when the mechanism is exactly at singularity. This is the difference with all 3. So now we can generate it 4 types of trajectory, which is here, degree 1. This is a simple linear equation, time function, degree 3, 5, and 8. Let's see if we plot this degree. So this is not the results yet. This is time function, sorry, the displacement in terms of function, in terms of time, I'm sorry. So here the degree one is simple straight line, which means in 0.2 second I will be here, in 0.4 second I will be in this position, I will be in this position, and etc. This is simple straight line. And then degree 3, here is to reach this point, I will go slower than this displacement, right? If you see this curve. And also here is also degree 5, I will go slower first, then I will go a bit faster, then finally go slower. And here it is, my new trajectory of degree 8. I will go quite fast first until I reach singularity, then I finally will go slower to compensate the previous velocity and accelerations. Then I will go to 0.6 and go back close to the singularity. This one is actually a compensation. Maybe you can hear the mosque here. I hope it doesn't bother you. And next, how the forces of my motors behave when it crosses a singularity for degree 1 trajectory. You can see the forces distributions. I hope you can still hear my voice. Okay, so this is the force distribution for motor 1. It goes up to infinity, which means this is very uncontrollable. You will need a very big motors to control your motions for crossing singularity. And likewise for leg 2, 3, and 4. And then for degree 3, the same, still in singularity, you need a very big forces to cross the singularity. And for degree 5, it's still happening. So your mechanism will still be shaky because you don't have enough forces to control the motion in singularity. Now, how about degree 8? So degree 8, if we see here in the left bottom picture, we have a singularity point at time 0.3, here 0.3. So if we see the force distribution at time 0.3, here it is actually controllable. So our algorithm works perfectly, which means my mechanism can cross singularity without shaky motion. Now let's compare all four trajectories. What happens? So we have trajectory 1, 2, 3. They are all have shaky motions and uncontrollable motions. But in trajectory 4, degree 8 at singularity 0.3 second, which is here, is controllable, which means this algorithm can be applied to my mechanism. Okay, so that was all about reconfigurable mechanisms. I want to share a little bit about type synthesis of a hybrid 2D graviton mechanism. I'm sorry. So if we take a look in the left video, this is the industrial application for cutting. So usually in industrial application, we will use a simple gantry frame, right? So the gantry frame is a planar mechanisms, and it will be subjected to bending. So now we want to reduce this effect, the bending effect, by using the hybrid mechanisms, the hybrid architecture. So this mechanism will still have a planar motion, but the architecture is spatial. So can you imagine it? So you have a spatial architecture. So we can see it here in the right video. So this mechanism, it has a hybrid architecture. Why? Because first, in the proximal leg, it has a parallelogram, but in the distal legs, it has a spatial architecture. This is probably not quite clear, but the motion is still 2-degree of freedom. The motion is still planar, but the architecture is spatial in space. Then we want to design another mechanism which exhibits the same behavior, hybrid architecture, but the motion is 2-degree of freedom motions. We are using screw theory, and you can see this theory in the book of Goslang and Xian Kong about type synthesis. There is a very systematic approach how to design a mechanism by using a screw theory. And we derive first, we have a platform, we have a base, we want to connect them together by using a leg, kinematic chain, and this kinematic chain should have a spatial architecture. We call it distal module, distal leg, and proximal module. And here is the process of type synthesis of my mechanisms. First, we define the platform, we define the base, we define the very simplest kinematic chain that connects both of them because it has a 2-degree of freedom translation, then it can be depicted by PP, prismatic virtual chain. And then from here, we came up with many design. So actually I put it in the wrong slide, so I will go jump directly just here. Okay, so here is our design. So let's take a look here. The shape just like a spider probably, but the platform, so if I fix the top as a base, so if I fix this top as a base and I move the below part as a platform, so this platform will have only 2-degree of freedom motions. I have an animation here. Yeah, this is an animation. This was published in 2014. So the platform will have only 2 translational motion, to the left, right, and up and down. But you see the legs, they are completely spatial. So if you put a cutting tool in the platform here, you will be free of a bending effect. And then with the same approach, systematic approach, we came up with the robots that I have shown you previously. This is actually the architecture of the robot. So the proximal module is composed of a parallelogram, and the distal module is composed of a completely spatial loop, spatial kinematic loop. This is UU. And this was patented in 2012. And I will go back a little bit. The last of my talk will be about cable robots. The last of my talk will be about cable robot. I will show you this is taken from internet, and I didn't have quite time to give the reference, so I hope there is no issue about that. So this robot was designed in France by Technalia. So if you see, it's like floating. There is no rigid links at all, but actually there are cables. There are so many cables, and this we call it cable robots. The advantage, you see, this is the cable. So the advantage of cable robots, it is light, but it can lift very heavy parts. I will go quite fast. So this is for material handling in an aerospace industry, and this is for painting, brushing the large structure by using a cable robot. This is for material handling using a cable robot. And this robot is named Kogiro. I think it's the name of their project, so they named this robot as a Kogiro. So I'm not doing anything. I don't have anything to do with this robot. That robot was just to show you the idea of cable robot. So what I'm doing here, back here with my colleagues, is we are building our own cable robot here. This will be used also for manufacturing and a small material handling, pick and place. So we are using 4 cables. Then what we are analyzing is the reconfigurability of the pulley. Now if we change the direction of the pulley, how this robot behaves. And not only that, we also change the configuration of the cables. You see in the right picture here, there is a blue lines. These are cables. So we analyzed if I don't know anything about cables, I will just assemble my cable robots just like this. But actually it has drawbacks, because exactly at this point up to the top vertically, they are always in singular configuration. So your robot will be always shaky. And now I have to change the configurations. I have to change the cable arrangements to be like this. So the cable cross to each other like this. You see, now in this configuration, I mean in this cable arrangement, my platform, when it is in this position up to the top vertically, it is no longer in singularity. So this project is a collaboration project with my partner from France and has been published 2020 this year. If you want to look at it in more detail, we are working on its dynamics and control, more about trajectory planning. You can take a look at the journal if you want to see in more detail. And then we are moving from that. We have a new concept here in my country, here Indonesia. We are sitting exactly at the Pacific Ring of fire. There are many earthquakes, natural disasters, landslides, and so on. So usually up to now even, we are dealing with it by using manual works. It takes quite some time to recover. Even we are using a simple bulldozer crane. So instead of doing that, we still have a collaboration with France. Now we will introduce a concept of cable robots, but by taking advantage of the available mobile cranes, the available cranes in the disaster site. So this is the concept. 4 cables all together, they are joined all together, lifting the debris, lifting the victims. This is what we are doing, and this is still going on. We started from the theoretical approach by analyzing its workspace. So at the top is the workspace of the robot, where the platform can move freely without having singularity, without having tension, too very high tension. And then here at the bottom, you can see the workspace is decreased, is reduced. Why? Because we are considering the stability of the mobile cranes. This is very important because my frame now is no longer fixed like before with the box frame, but my frame now is based on the mobile cranes. And then if I lift very heavy debris, my mobile cranes can collapse. Do I still have time? So I will show you the last video. This is to show you. Okay, so this is our simulation. You see, at some point, one mobile crane cannot afford a very heavy load, so the mobile crane collapsed. Now, if we introduce the notion of reconfigurability, so we change the angle, the length of the telescopic boom, it can execute the task perfectly. Then, if we change the trajectory to be like this differently, again, it will roll over to different directions. The mobile crane. Now let's see the right animations. We introduced the notion of reconfigurability of the telescopic boom. Then the trajectory can be followed perfectly. Right, that's the end of my talk. I took a quote from Marie Curie. I believe you all know she was a Nobel Prize winner in physics, both in physics and chemistry. She's the only one. Nothing in life is to be feared, it is only to be understood. Now is the time to understand more so that we may fear less. You can check if you want to check in more details about my research in our lab website, or you can check my YouTube channel. I put some videos, even the videos I presented here, I put it in my YouTube channel. All right, thank you very much.
Thank you, madam. We will wait for 5 minutes if any participants have any questions or something.
Please feel free if you have any questions.
Ma'am, can we have collaboration for setting up a robotics laboratory at our institute with your institute?
Yes, of course. I would be very honored if I can contribute something to your future lab.
Okay, okay. So we'll discuss later on how to go ahead with this collaboration. And
Yes, you can.
any can we have any virtual lab at your institute so that our student can be benefited from that? Any
Um,
virtual lab at your institute?
I think that would be possible. We can discuss about that in more details. How virtual that is, the lab that you want it to be, because at the moment the school is still closed. But
Okay.
for, let's say, for joint supervision or other things, my students can also collaborate with your students. I think it is possible.
Yes, yes.
And you can
Okay.
contact me through my email. Here is my email. Both emails are active.
Okay. Thank you, madam. Thank you.
You're welcome. Thank you very much for your interest.
Thank you so much, ma'am, for this wonderful session on all the aspects like kinematics, mechanism, metamorphic parallel mechanisms, dynamics, type synthesis, cable-driven parallel loaders, and all those aspects. I hope all those participants and all those speakers who have also present in the meeting must have benefited and got some kinds of insights from this presentation. And we will be in touch with you, ma'am, for any further association or collaboration or any kind of similar sessions, if possible, in future. And we wish you good luck and very thankful to you, ma'am, for giving us your valuable time.
Yeah, thank you very much for inviting me to give this talk. I hope what I gave to you is very useful for you. I hope it is useful for you all. And thank you again.
Thank you so much, ma'am.
Thank you. Thank you.
Thank you, everyone, and hope you all stay safe. And we will have our session again at tomorrow, 11:30 a.m.
Okay, thank you, madam. Thank you.
Thank you. Have a good day.
Have a good day.
Bye bye.